So we'll continue on with the respiratory system review. Here are the 6 objectives for this little lecture. So we're going to start off with the 8 main volumes or capacities. And as we go throughout the semester, and specifically when we're talking about the cardiorespiratory systems, we'll get into how these change a little bit. Now, just to orient you to this figure, we've got volume on the y-axis. X-axis, there's really nothing. We're just looking at how these volumes change or what they consist of. Okay, and so as we go up, as volume increases, that's taking a breath of air in, or in other words, you have more air in your lungs. As you go down, there's less air in your lungs. Okay, this line down here that's not highlighted, there you go. That's when we get out as much air, or we exhale as much as possible. Okay, so here we've got what's called tidal breathing. So breathe in, breathe out, breathe in, breathe out, breathe in, breathe out. Okay, so that's what this little yellow is, just normal tidal breathing. Now, if we go from the bottom, so we normal exhale, and then we breathe out as much as we possibly can down to here, that's expiratory reserve volume. Or in other words, when we take a breath of air out, how much more air could we get out? Now, we'll eventually get to a point where we can't get any more air out, but there's still air in our lungs, and that's residual volume. Okay, so there will always be some amount of air in your lungs. And this is because as you generate pressure to exhale, you collapse some of your small airways, and there's air trapped behind them, and you can't get it out. We can't actually measure this directly. We have to use some special equipment to essentially estimate. Okay. Now, similar to expiratory reserve volume, we have something that's called inspiratory reserve volume. And so inspiratory reserve volume is where we take a normal breath of air in, so right here, and then we fill up our lungs as much as possible. So, take a breath of air in, how much more air could I get in? What's reserved? What's left? Okay. Now, something very similar to that is inspiratory capacity, but this one goes from here, so we take a normal breath of air out. It's time to take a breath of air in. How much can we actually get into our lungs? That's inspiratory capacity. Now, at the end of a normal breath out, we've got an amount of air in our lungs, okay? And so that goes from here down to here, and that's what we call functional residual or functional reserve capacity, okay? This is where the pressure of your lungs wanting to contract and your ribs wanting to expand is equal and opposite. So that's kind of like the sweet spot, the happy place. That's actually why we stop breathing at that point, okay? And then we've got vital capacity. And vital capacity is the maximum amount of air you can move in and out of your lungs. And so in order to do this, we have to fill our lungs all the way up, and then we breathe out as much as we possibly can, and we go down here. Okay, so that's vital capacity. And then the last one is total lung capacity, and that's just how much air is in your lungs when they are completely filled up. Now, there are a couple types of ventilation that we're concerned about. And you have to remember that when we breathe in, the last amount of air that's breathed in or that you take into your lungs is going to be the first bit of air that comes out. Now, when you breathe in, not everything makes it to the alveoli, which means you don't have gas exchange. And so the air that doesn't undergo gas exchange, we refer to as dead space. And so just using typical numbers, let's just say our tidal volume, okay, normal breath is 500 mils. Well, the dead space is 150 mils. And so that means 350 mils, or 70% of the air, is actually reaching your alveoli and undergoing gas exchange. Now, we can increase tidal volume, but we can't increase dead space. So dead space is like your trachea, your big bronchioles, your big airways where gas exchange can't occur. And so we can calculate minute ventilation, and we can also calculate alveolar ventilation. So minute ventilation is just how much air you're bringing in and out of your lungs every minute. And then alveolar ventilation is how much air is actually undergoing gas exchange every minute, okay? And so with alveolar ventilation, we have to account for that dead space, okay? And that would be the 150 mils. Now, if I ever ask you to calculate dead space ventilation, or excuse me, alveolar ventilation, I will let you know what dead space is, okay? Now, with the respiratory system, the job is to get, or one of the main jobs is to get oxygen into the bloodstream and take CO2 out when we're talking about pulmonary capillaries. And in order to do this, we have to have gradients. Now, from what we talked about in PE 220, so your introductory human phys class, we just assume that alveolar and arterial oxygen are equal And the same is true of alveolar and arterial carbon dioxide, that they're equal. Okay, we'll talk about it in about 5 or 6 weeks. This isn't actually the case, but just to make things simple, we're going to assume that that's the case. However, blood that's in the veins has a pressure of about 40. Oxygen has a partial pressure of about 40. And so what happens is oxygen wants to go from the alveoli into the bloodstream. And so then that's how we go from this 40 to 100. But when we're talking about CO2, we've got 46 in the veins, which is the venous blood or deoxygenated blood that returns to the pulmonary circuit. And so CO2 goes this way. Now, the reverse is true in the systemic system. Okay, so we've got high oxygen in the arteries, low oxygen in the tissues. And then we've got high CO2 in the tissues, low CO2 in the arteries. And so the direction of travel is different. So CO2 will go into the bloodstream, oxygen will leave the bloodstream. And so diffusion is affected by 4 things: the pressure gradient, the surface area, the thickness, and then also something called a diffusion constant. Gases diffuse differently in different solutions. CO2 actually diffuses more rapidly, more easily than oxygen. Okay, so as that constant goes up, that just means diffusion occurs more quickly. But the pressure gradient, so the bigger the gradient, the faster the diffusion will occur. The more surface area, the faster diffusion will occur. The thickness, or the distance that it has to travel, the slower diffusion will occur. So this is the formula for diffusion, the rate of diffusion. You'll never have to calculate anything, but you should be able to use this formula to understand how different conditions can affect the rate of diffusion. So, for example, we've got 4 different conditions here, and we're just looking at our alveolar. So big A is alveolar, little a is arterial. What's that going to do to the amount of oxygen in both of these? Okay, so for example, if I have emphysema, which means I have fewer alveoli, my alveolar oxygen will remain the same. Just because I have fewer alveoli doesn't mean that the partial pressure of oxygen that I inhale is any different. But my arterial oxygen will decrease because I have less surface area. Now, if I have edema, which means I have fluid in the interstitial space, so in between the alveoli and the capillary, again, that doesn't affect the pressure of oxygen going into my alveoli, but because it's a greater distance or greater thickness, the arterial oxygen will be decreased. Similarly, fibrosis is essentially the same thing. Okay, so now I've just got a thicker alveoli, which means greater distance that oxygen has to travel. So my alveolar oxygen will remain normal because I can breathe in normally, but my arterial oxygen will decrease because not as much diffusion will occur. The last one is asthma. So I've got decreased resistance, which means it's going to be more difficult to get air in and air out of the alveoli. So I have a lower alveolar oxygen, but I'm also going to have a lower arterial oxygen because I have a reduced gradient. Okay, next we have oxygen transport. So there's 2 ways that oxygen is transported. We've got hemoglobin, which is where most of our oxygen is transported, so about 97%. This is what we measure when we measure saturation. And then we've got dissolved in plasma. We measure this by taking the partial pressure of oxygen in the plasma. That's about 3% of the oxygen. Saturation is much, 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 much more important than partial pressure. The crazy thing is we don't have a saturation sensor in our body. We have a pressure sensor in our body. And this leads to the oxyhemoglobin dissociation curve, which shows the relationship between partial pressure and saturation. Okay? Notice it's not linear. It's what we call a sigmoidal curve, and this is due to the relationship between hemoglobin and oxygen. Okay, hemoglobin one molecule of hemoglobin can hold 4 molecules of oxygen. When it's completely empty, it's hard for oxygen to load. When it's completely filled, it's hard for oxygen to leave. Okay, and so there's a whole analogy with Mean Girls that we'll discuss in class that will help you understand it, hopefully. Now, we can also affect this curve. We can shift it left or shift it right. Now, when we shift it left, we increase the affinity or attraction between oxygen and hemoglobin. And so what that means is that for a given partial pressure, I'll have a higher saturation. If I have a right shift, that's going to cause a decreased affinity or decreased attraction. So then for a given partial pressure, I'll have a lower saturation. Okay, and there are this is affected by temperature, acidity, and carbon dioxide. If I increase any of those variables, that will cause a right shift. If I decrease any of those variables, it will cause a left shift. And we'll get into that a little bit more in a couple weeks. But just know that this thing is important, right? Basically, what happens, especially with acidity and carbon dioxide, they'll take up a spot on hemoglobin. So if carbon dioxide is bound to hemoglobin, that's one less spot for oxygen to bind to. And the same is true with acidity, but instead of carbon dioxide, we're talking about hydrogen ion. Okay. Apparently, I repeated this, so not sure why that's there. So with carbon dioxide, we transport, most of it is bicarbonate, and some of it's dissolved in plasma, and some of it's bound to hemoglobin. We've got this equation, carbon dioxide plus water turns into carbonic acid, okay? And just so we're clear, it's not carbonic acid bicarbonate, okay? Bicarbonate, the carbonic acid breaks down into bicarbonate and hydrogen ion. When we're in the lungs, it moves towards carbon dioxide. When we're in the tissues, it moves towards bicarbonate. The reason being, we exhale carbon dioxide in the lungs, and we want to turn this to bicarbonate in the tissues so we don't take up binding spots for oxygen. Okay? And so we've got these three ways here. So again, dissolved in the plasma, bound to hemoglobin, so CO2 leaves the tissues, combines with hemoglobin, and then a bunch of it will also diffuse onto the red blood cell, combine with water. And when it combines with water, it forms that carbonic acid, which is here. That carbonic acid breaks into bicarbonate, and bicarbonate will leave the cell and be dissolved in plasma. When we get back into the tissue, or when we get back into the alveoli, everything reverses. So the stuff that's dissolved in the plasma will diffuse in the alveoli. We breathe it out. The stuff that's bound to carbon dioxide breaks down, and so the carbon dioxide leaves the red blood cell, dissolves into the plasma, which diffuses into the alveoli. We breathe it out. And then we've got bicarb, and that entire thing reverses, dissolves goes into the plasma, dissolved to CO2, diffuses in the alveoli. We breathe it out. Okay. I realize that especially with these review ones, I've kind of flown through them. So again, if you have questions, come to class with questions, or you can ask me for links to old videos if you can't remember or need a little bit more detailed and probably a little slower review. But with that, we are going to end.